and today we're going to be looking at matrices and matrix operations. And for those of you who were excited yesterday when we were looking at systems of equations, which was your do now for today, we're going to gradually get back to systems of equations by way of matrices, but we need to build our way there. And so, since we need to build our way there, we first need to have an understanding of matrices and what we can do with matrices in the first place. So that's what our objective is going to be, is how do I add, subtract, multiply, and use scalar multiplication for a matrix, or matrices. Well, if I'm going to answer that question, my first thought is, well, gee, what in the world is a matrix in the first place? And a matrix is nothing more than a two-dimensional array of numbers or terms. Because sometimes we don't always have simple numbers in our matrix. Sometimes we actually have variables. And so a matrix is a two-dimensional array of numbers or terms. You can even think of them as a two-dimensional collection of numbers or terms. And what does two-dimensional mean, Ms. Watson? Flat. Two-dimensional means flat?
Not, I don't know, I can't think of it. I just know it's like a shape that you just, like a normal square, like, if that's an example. Can I give you an example?
Well, you can define, we're going to define it with an example. So Ms. Watson says two-dimensional means like a normal shape, a square.
Like that you draw on the board.
Let me ask you a question then, Ms. Watson. What's three-dimensional?
Like a cube.
A cube is, so what's the difference between a cube and a square?
I know the difference, but it's like I can't think of the words to describe the difference.
You want to get some help from someone? So, let's say it louder.
Third-dimensional object.
Three-dimensional.
Three-dimensional object has height and take up space.
So, a three-dimensional object has, what are the three dimensions?
Height, space, and texture.
Not texture. Some of your classes want to help you there. You got almost two of them. Ms. Garcia. Height, length, and width. And sometimes we think of that width, and we don't really say width. Sometimes we say depth. So a person is three-dimensional because I have a length, I have a width, and you can't just look at me and then there's nothing on the side of me. Like there's a depth there. So people are three-dimensional, but when we're looking at a matrix, Ms. Watson was there, a two-dimensional matrix is very much like a square. It only has two dimensions, a length and a width. And if we were talking about three-dimensionals, we get into having that depth, or as Mr. Lynn said, taking up actual physical space. So, two-dimensional array of numbers or terms. Well, I need to be able to describe a matrix. And so that brings us to our next term, which is an order. An order, and you'll also see dimensions. An order is the same as a dimension. To get the order of a matrix, we say a matrix is of order m by n. Gee, Mr. Whitfield, what is m? M is the number of rows, and n is the number of, someone said it, number of columns. So if I need to know the order of a matrix, you just need to tell me the number of rows and columns and I can tell you. So here's a good example. Let's see if someone is picking up on this. Let's say you're given this matrix. Let's say this is matrix A. 2, -1, 4, 6, 0, -5. Volunteer, please. What is the order of matrix A? Volunteer. What is the order of matrix A? Given what we have just seen. The matrix is of order m by n. You told me what m and n were. Ms. Irving. Thank you for volunteering. You're so kind. What is the order of matrix A? Say it again. 2, 3. 2 something 3. How did I say this? Not 2 times. 2 starts with a B. Ms. Roberts wants to help you if you're stuck. Or 2 by 3 matrix. So yes, it looks like a multiplication symbol, I know, but we say 2 by 3. So I know that this is a 2 by 3 matrix, Miss Walton. Why? Because it, non-descriptive pronoun. Thank you. Matrix has 2 rows and 3 columns. So we know what a matrix is. We know how to describe the matrix. But now let's say I want to look at my matrix and I want to be able to tell you what a certain term in my matrix is. So inside of matrix are absolutely terms. And that's a math term everyone should be able to, look at that, math term, finding a word with the word. That's a math term that everyone should be able to know and hopefully understand what a term is. But I have a 2 by 3 matrix, which means how many elements are in this matrix? There are 6. There are 6 elements in matrix A. But I don't want to have to, every time you want to look at a certain term or an element, look at the matrix and say, look at the 0. How we label or identify our terms is we take the matrix name and then we have MN. So this is the name of my matrix. M refers to the row of that term. So if I need to identify where someone is, I first start with the row, and N then tells you where and what column is that term. So this is how I identify where my terms, or another word, where my elements in my matrix are. So let's see another example of that really quickly. Let's say you're looking at this same matrix A. If I told you to look at, I don't know, the 4, how would you identify the 4 in matrix A? Ms. Clark. Yes, ma'am. A13. Because the 4 is in, why did she say A13, Mr. Orr?
In the first column,
Because
in the first row, because 4 is in the first row, third column.
Thank you. So the position of the 4 would be A13. How are we feeling so far? Okay? Wide, got it? Wonderful. So we understand what a matrix is. We understand how to identify the size of my matrix. I even understand how to look at a matrix and then pull out or tell you to go to a certain term. So my next step is to say, okay, well maybe there's something more I can do algebraically with matrices, and there are. Just like with functions and numbers and values and math, guess what? We can add, subtract, multiply, and we can even sort of divide matrices. So let's start with addition. Let's say I want to add and or subtract matrices. There is one very special rule, ladies and gentlemen, in order to add or subtract matrices. Your matrices must be the same. One, I'm going to add or subtract, they have to be the same. Not term. Someone said it. Not row, same order. My matrices, if I'm going to add or subtract them, I can only do that if my matrices are of the exact same order. So, I can only subtract a 2 by 3 matrix, Mr. Honeycutt, from another what? From another 2 by 3 matrix. So, let's take a look at an example. We can do addition or subtraction. Let's start with addition. Let's say you were given the matrix 4, 1, 0, and someone told you to add that to 3, 2, 1. So I need to add these two matrices. Miss Watson, what's the order of this first matrix here? And I'll call them A and B. So what's the order of matrix A?
The order.
Yes, ma'am.
The order is, oh, A and B, right? That's what you mean?
Is that what I mean?
No, order. Oh, the matrix. Okay. It's a 3 by 1.
Thank you. Why is matrix A a 3 by 1 matrix, Miss Watson?
Because it's 3 rows.
Because
Because the matrix is 3 rows.
Perfect. Mr. Beckwood, what is the order of matrix B? How do you know? It looks just like A. That's not going to cut it. it.
I mean, the matrix has
Thank you. So can I add these two matrices, Miss Roberts? Yes, ma'am, I can. Who do you think, Miss Walton, I'm going to add the 4 to? I'm going to add, why? Well, if you had to tell them, why do I think I'm going to add the 4 and the 3? Why? It must be in the same order.
It must. Why would you add? Because the 4 is corresponding to 3.
I like the way you phrased that. The 4 in matrix A.
It corresponds with the 3 in matrix B.
Perfect. So 4 plus 3 would then be?
10.
And then who would I add the 1 to, Miss Irving? I know. Look, it's like, oh, this is too easy, Mr. Whitfield. And last but not least, Mr. Honeycutt. 1. The 0 plus 1. So your resulting matrix, I have a question, Mr. Lynn. What do you notice about the size of that last result? Or the order of that, our answer? What do you notice about it?
It's the same
The same as who?
as A and B.
As the what of A and B?
The order of A and B.
So, the size of my result, whenever I add or subtract, I expect it to be what?
The same.
The same as
The matrix A and B.
whatever two A and B in this case, but whatever matrix I add or subtract. Next, let's look at scalar multiplication. This is again, if we can multiply an entire constant times a function, Mr. Orr, guess what? I can multiply an entire constant times a matrix. So, Miss Garcia, let's say I gave you -3 times 2x minus 4. What would you do? You would distribute the -3 to whom? And so, what would your result be? Do you agree with her, Mr. Beckwood? Thank you, Ms. Garcia. Do you agree with her now, Mr. Beckwood? Okay. So, just like I could do that, I could come down here and say, if I'm giving you some constant, we call the constant in matrices a scalar. If I give you some scalar times some matrix, I can call this matrix B, and let's call these terms, we can give them random numbers, 6, 4, 1, 2, 3, -2, 5, 1, 4. If I'm multiplying a scalar times this matrix, then I would need to multiply the scalar times who, Ms. Watson?
8.
Times, this is the scalar is A. Who am I?
mean, by the whole entire matrix?
By the entire matrix, or by every what?
Element.
By every element in my matrix. So, what size is matrix B? What is the order of matrix B, Ms. Clark?
3 by 3.
It's a 3 by 3. How do you know that it's a 3 by 3 matrix, Ms. Roberts? Perfect, because my matrix has 3 rows and 3 columns. Well, if I multiply the entire matrix by A, my first term is no longer -6, it's who? -6A. My second term becomes 4A, and then A, what do you notice, Mr. Lynn, about the size of this matrix compared to what I started with?
Yeah, always correspond to the same matrix.
Say it again?
Always correspond to the matrices on the other side.
We're getting into a battle of words with ourselves. The order of my result is what?
It's the same and one the matrix on the other side.
The order of the original matrix I started with. Yes, sir. The order of my result is the exact same as the order of the matrix that I started with. So, we've covered addition and subtraction with a little, I know we only saw addition, but I really do trust, Ms. Irving, that you can subtract 2 numbers. I trust you. Then we looked at scalar multiplication. And so now, we looked at addition, we looked at subtraction, sort of, scalar multiplication. Now let's go to looking at an identity matrix. An identity matrix, ladies and gentlemen. Because sometimes the world would be perfect if I if I had a standard, like a standard matrix that I could always count on. That's what we get in identity matrix. And an identity matrix, first and foremost, must always be, this is my first guideline, must always be n by n. I just put n by n. What does that tell you, Mr. Honeycutt? If someone said this, an identity matrix has to be n by n, what does this look like to you that we've already talked about? It looks like the order. And what do you notice if I said n by n? What do you think I'm really trying to tell you about this matrix?
You must always have the same amount of rows and columns.
Thank you. That an identity matrix has to have the exact same amount of rows as it does columns. Well, there's only one other item. I know that I must be an n by n matrix, and that the diagonal, and this is the main diagonal, must consist of only ones. We're going to see some of you are looking like, I don't know what he just said. The main diagonal in my matrix, that is n by n, can only have ones in it, and all other terms or elements must be zeros. So, n by n matrix, the main diagonal has to be all ones, and all other elements in that matrix has to be a zero. So if I said to you, Miss Irving, I want you to tell me the identity matrix that is 2 by 2. Well, how many rows and columns does this matrix have, Miss Irving? 2. Well, I did the first guideline, I hope. Do I have the same number of rows as I do columns? Yes, I do. Then what was the next condition? Wait a minute, who must only be ones? The diagonal in my matrix. Well, for a 2 by 2 matrix, with this, if I put ones here, would that be a diagonal, Miss Irvin? No, that would actually be a what? In terms of what we know about matrices. Is that really a column? I think that might be a row. So where would you put the 1 or the ones in a 2 by 2 matrix? Volunteer. Where would I put, if I know that my ones have to be on the main diagonal, where would I put the ones? Yes, ma'am, Miss Watson? Keep in mind, Miss Watson, we know how to tell us position now in a matrix. This is I.
I will put my first one at I1, 2.
I1, 2.
No, that's okay. This row. No, I1. Okay, let me see. I'll put it at row 2, 1. No, I2, 1.
I2, 1. So that tells me what?
Then I will put it in row 2 on column 1.
So
Right there.
here.
Yeah. That's right.
How many of you agree with Miss Watson? Your classmates are hesitant to agree with you. Hold on. Miss Garcia, your thoughts?
I agree. Thank you, Sonia.
Yes, sir?
I would put in I1, and then the other one at
I2, 2. So Mr. Honeycutt says he would actually put his ones at I1, 1 and I2, 2. How many of you agree with Mr. Honeycutt? Mr. Honeycutt is correct. Your main diagonal, and this brings up a good point. Miss Watson, if this is my main diagonal, I must go from where to where?
Left to right.
From upper left to bottom right. My main diagonal, we can add that in, is from upper left to lower right. So, I have all ones, everyone else must be who? Must be zeros. And this is your identity for a 2x2 matrix. On your paper, please, give me the identity matrix that is 3x3. On your paper, give me the identity matrix that is a 3x3 matrix using the same guidelines. I need to have an n by n matrix, and I know that my diagonal, my main diagonal, has to be all ones. Everyone else has to be zeros. Thank you. Thank you. 3x3. What is 3x3? Thank you. Thank you, Ms. Clark. Thank you. Thank you, Ms. Garcia. Oh, I left off a word. Thank you. Thank you. Yes, sir. How many rows and columns should you have? Should you have 3 rows? And how many columns do you have here? Oh. Thank you, Ms. Watson. Thank you, Ms. Roberts. All right, ladies and gentlemen, that's pretty much where we want to stop here for today. The last thing I want to do, and you're going to need your calculators, please, I want to show you how to make your life so much easier on your calculator. So, if you would please, take out your calculator and turn it on, because there's no need of taking out a calculator that's not turned on, right, Mr. Orr?
Great.
Correct. I know. So, I don't always want to be doing matrices by hand, Miss Walton. And I know how much we love our calculators, don't we, Miss Walton? Yes, we do. And so my concern is maybe there's a way for me to perform matrix operations on my calculator. And there are. My projector. So, I think this will do it. I hope. Like magic, did it happen? It happened. All right. So let's say you want to perform matrix operations in your calculator. Let's say, and everyone, let's look at an example in our book. If you would go to the exercises, please, for section 7.2. Let's say you want to look at exercise number 11. Everyone is there in your book, exercise number 11. Thank you. So we're looking at exercise 11, and what am I told? What is the first thing I am supposed to do for exercises 11 through 16, Mr. Orr? Matrix A and B need to be added. So ladies and gentlemen, on your calculator, if you press second and this x to the negative first key, what do you notice? You get different types of matrices. And my, oh, God, help me. Where am I? Hopefully that, I had to start mine over. I'm sorry, ladies and gentlemen. It's being a little fickle. No, it's not. Look at that. So, here we are. I think I can do this now. There it is. Second matrix. Now, rather than hit enter at A, because this is what everyone's screen should look like, we need to scroll over to where we can edit our matrix. So everyone should scroll over to edit, and now hit enter. Now, what is the size or the order of the matrix A? It's a 2 by 2. So what should I make this matrix here? 2 by 2. And you should notice that your matrix magically becomes a 2 by 2 matrix on your screen. Now, let's put in the elements. Please make sure you put them in the correct order. 2, 3, -1, enter, 3, enter, -1, enter, and then 5. So I have matrix A. Guess what I'm going to do now? I'm going to exit this, so I'm going to go to second matrix again, and now who am I going to edit? Matrix B. So I'm going to come down to matrix B and edit matrix B. What size is matrix B? Also a 2 by 2. And again, you notice that your matrix is changing to a 2 by 2. So now I need to put in these elements. 1, -3, -2, and -4. Oh, I put in -4 twice, didn't I? There it is. Thank you. So now I can exit, ladies and gentlemen. So I'm going to do second quit, and I am back at my home screen. But Mr. Orr just told me, what was I supposed to do with these two matrices? Add them. So your calculator is so nice to you, it says, okay, second matrix. So I'm going back here. And now look at A and B. They are both what?
2 by 2.
2 by 2 matrices. I can now hit enter for A plus who? Matrix B. And when I do, look at what your calculator does. It says, bam, there it is. There is matrix A plus matrix B. I can even do scalar multiplication. Let's say I wanted to know what was 9 times matrix A. I can just put in 9, second matrix, option A for matrix A, and look at that. It tells me what the scalar multiplication is of 9 times matrix A. But just wanted to show you how your calculator is able to do exactly what you are able to do. How are we feeling? Still good? Liking matrices so far? Kind of hate it? Love it? Wish you could take them home with you? Play with them all night? Okay, so that being said, let me tell you what your classwork is. Your classwork for today, ladies and gentlemen, I would like for you to do from section 7.2 to be turned in before you leave. Problem number 8, problem number 12, all parts, and there's one more. I think that's it. 8, 12, and, oh, I forgot one. Number 2, 8, and 12. There it is. So you're going to do that independently. Ladies and gentlemen, before you get started, I need to make sure that you have written down your homework. 3 through 33, multiples of 3. Are we clear?
Yes, sir.
Thank you, thank you. Yes, ma'am. You may. Thank you.